So a true differentiator circuit, the concept is it is going to take the input, take the derivative of the input, and the output is going to be proportional to the derivative of the input. That is, derivative of the input times some sort of gain of the circuit. That's what true integrated circuit does. Observe that all we did is we switched the position of R and C. For the integrator circuit, true integrator circuit, C was in the feedback loop, R was in series with the input voltage, and in this case, of course, we switch those two components. So if we analyze this again with our usual analysis, that the current going towards the virtual ground will be equal to the current going through the feedback loop. Then we can write down. Of course, again, there's a capacitor here. So whenever you have capacitor, you use the capacitor voltage equation. That is, the capacitor current is equal to C times derivative of the capacitor voltage. In this case, the capacitor voltage is V input minus 0. So simply V input. And the output and the current through the feedback loop is 0 minus V output over R, or negative V output over R. So again, we arrange this in terms of V out, and V out in this case will simply be negative RC times dVit over dt, as simple as that. In integrator circuit, remember, you have to first integrate the equation to get V output. In this case, of course, you don't have to integrate the equation, and the output is equal to gain of the amplifier, which is negative RC times derivative of the input. Now, true differentiator, there is one problem, like there was a problem with the integrator circuit, there is one problem with the true differentiator circuit as well. And the problem is, anytime you have noise at the input, remember, the output is the derivative of the input, that is rate of change of the input. So anytime you have a small spikes of noise at the input for a very brief amount of time, the dVi over dt is going to be very large, right? Because the shorter the time is, the larger the spike is going to be, because you're taking derivative of that. Hence, the output for a small noises, output can have substantial amount of noise spikes. And just for this reason, we don't really use the true differentiator circuit in practice. I mean, we can still use the true integrator circuit, but true differentiator circuit is hard to be used in practice, because of course you will always have small noise spikes at the input, and those noise spikes can produce a very large output. Of course, it will saturate. It's not going to go beyond 15 volt, but it's going to be still a big spikes. As the frequency increases, gain of this circuit will increase, as you will see shortly when we do the AC analysis, and you will have even more spikes when you have higher gain of the circuit, that is at higher frequencies. So that's another problem with this circuit. So and again, just quickly, if your input is a constant DC, of course, when you take the derivative of a constant DC, the output should be 0. If your input is a square wave, you can have impulses at transition. Remember, you have a square wave. So that only time you have, of course, the output will be 0 when it's a constant value. But when it is going from 0 to 1 or 1 to 0, then you can have derivative of this is going to be impulses, because remember, the derivative is what you are calculating, slope of the line, and slope of this line is infinite. So when you have the transition, then you can have spikes, and then 0, and then a spike again, and then 0. Triangular waveform, that is your t signal, A times t, is going to produce a constant signal A, right, when you take the derivative of A times t. And sinusoidal waveform will still produce a sinusoidal waveform. If you have a sine wave, then you're going to have a cosine wave at the output, and if you have a cosine wave, you're going to have a sine wave at the output. So this is just for the shape, because most of the time you're not really taking derivative. What you're doing, as you will see, you're calculating slope of the line, and then if you know the shape, you can always create the output or guess the output, how it's going to look like. Okay, let's skip this. We already discussed this. We're gonna go now to low frequency differentiator circuit. low frequency differentiator circuit. And why do we have low frequency differentiator circuit? Again, because as we discussed, a small noise spike over a very brief amount of time at the input can produce larger spikes at the output, especially when your frequency increases. That is going to increase as well. So what do we do? What we do is we include a resistor in series with the capacitor at the input. So remember, for the integrator circuit, the AC integrator circuit, we added a feedback resistor in parallel to the capacitor that was connected in the feedback loop. In this case, we will include a resistor in series with the capacitor, which was basically for true differentiator circuit. There was only capacitor at the input. Now we have a series of resistor and capacitor. So let's look at first what will be your derivative, what will be your phasor analysis of this circuit. So you take the series combination of input and X of C. That's your input impedance, or the impedance that is connected to the input voltage, and then your H of j omega. It is going to be, of course, again the circuit is still the inverting circuit, so your H of j omega V out over V in is equal to feedback impedance. In feedback, now you have input the feedback resistor, sorry, minus, and in the input you have Z in, right? So this will be the transfer function of the circuit, and then you go ahead and put Z input this value right here, and then you are going to get, after simplification, you're gonna get something like this. Now R input C is the input time constant Ti, and 1 over R input C. In this case, actually, you have two of them, RFC and R input C. Now, if you go down a little bit, first we calculate the magnitude of this. The magnitude of this is the magnitude of numerator divided by magnitude of denominator, right? Because it's a complex number in fraction form. So magnitude of numerator is omega RFC, and magnitude of denominator is 1 plus omega R input C squared, square root of that. Alright, in this case, the break frequency is 1 over R input C, right here. This is the break frequency, 1 over R input C, or 1 over tau I. That's the break frequency. So when omega is quite larger than the break frequency, right? When omega is quite larger than the break frequency, we will ignore this one. This one will be ignored, and we can write down magnitude of this omega RFC, the numerator, divided by omega R input C. And then, of course, omega will be cancelled out, C will be cancelled out, and you're going to get the magnitude RF over R input. What does this show you? That for higher frequencies, this circuit again is going to work as an inverting amplifier. Remember, this is just a magnitude, so it is not showing you the negative sign over here, right? It's just a magnitude. But it is working as an inverting amplifier with the gain of RF over R input when the frequency is quite larger than omega B. And why it is important? Because again, it is important because for the true differentiator circuit, as the frequency increases, your gain of the amplifier also increases, and the spikes will also increase because they are multiplied by the gain of the amplifier or gain of the differentiator. So in this case, if your frequency is increasing above omega B, you don't have that problem anymore, that your gain of the differentiator is increasing as well. Your gain is going to become constant, and circuit will start operating as an inverting amplifier instead of a differentiator. Now, if your frequency is quite smaller than omega B, then it is going to be, m omega will be approximately omega RFC. So this is the transfer function, the magnitude of the transfer function of true differentiator circuit, omega RFC, right? Because if I go over here again, right here, and if I don't have R input over here, then basically my gain is going to be negative R RF over XC, right? Or negative RF over 1 over j omega C, or negative j omega RFC. That's going to be my transfer function for the true differentiator circuit. So my magnitude for this is simply omega RFC. So observe again, higher the frequency omega, you have the higher frequency is you will have more spikes because your frequency is high, and of course the gain of this is going to be constant, but the total gain of the amplifier is going to be omega RFC times the input, so the output is going to be quite high at higher frequency. Now in this case, in the case of low frequency differentiator, we have solved that problem, because at higher the higher the frequency you have, your gain is not going to be dependent on the frequency. It's simply an inverting amplifier, RF over R input. Now when the frequency is low, then it's going to be working as the true differentiator circuit. The gain of the amplifier is going to be omega RFC, or the transfer function gain is the same thing, omega RFC. So your output is going to be omega RFC times the input. And if omega is a small, of course the output for stray frequencies, stray noise voltages, is not going to be that high at the output. Okay, now there is one problem here. Of course, we discussed in chapter number 4 that all the operational amplifier circuits, they have a closed loop bandwidth at which the gain of the closed loop gain of the circuit goes down to 70.7% of the maximum gain, which is at DC and low frequencies. The same thing is going to happen here. So when we are saying that when omega is quite larger than omega B, then the gain of the amplifier is going to become RF over R input. That is partially true, because when you're going to hit BCL, then of course your gain is going to start going down. So you cannot just keep increasing the frequency and assume that gain will always be RF over R input. It will be something like this initially. So it's going to be something like this. This is up to omega B. So in this range, it is working as a true differentiator circuit. And then this is your BCL. Between omega B and BCL, it is working as an inverting amplifier. And then after BCL, the gain of the inverting amplifier is going to start going down. Alright, so how are you going to figure out the output of a low frequency differentiator? It is quite straightforward. Negative RFC is gain of the differentiator at low frequencies when it is working as a differentiator, that is. And then when you're calculating dV input over dt, what is that? That's the slope of the input, right? So the easy way, one of the easy ways to do it is to calculate the positive slope and the magnitude of the negative slope. And then there should be an addition, it should not be a subtraction. So I made a couple of mistakes over here. That should be, let's see, I'm assuming there should be an addition. Let's see, 10, yeah, that should be an addition. I'm pretty sure there should be an addition. So I will fix this. That should be an addition. And positive the maximum, negative slope. Note that you're doing the magnitude of the two slopes together to determine, you're adding, yes, here. I'm not sure why I put a negative sign here. You're adding the two slopes together, magnitude of the two slopes together, to figure out the output peak to peak value. So you're going to take the positive slope and the negative slope, take the magnitude of the negative slope, don't take the negative sign, just the magnitude, and then add the two slopes together, multiply that by RFC, and that's going to be the output for the differentiator circuit. Of course, first you're going to calculate the frequency. It has to be quite smaller than omega B in order for the circuit to work as a differentiator circuit. And negative sign again tells you that if the input is increasing, the output is going to be decreasing, and vice versa. So this example, your input is a triangular waveform, and then you can go through this example, and the output is going to be a square wave. Remember, triangular wave is going to produce a square wave because triangular wave is AT, or A negative 80, and when you take the derivative of this, you're just gonna be get an A. So you're gonna have a positive A and negative A. When the waveform is going down, of course, the output will be high because of the negative sign, negative RFC, and when waveform is going up, the output will be low. And you calculate the negative slope from here, you calculate the positive slope from here, you add them together, you add the magnitude of both together times RFC, and that will give you total peak to peak output of 20 volt. The output will always be centered at 0. Why? Because any DC signal in the input waveform, remember, for DC signal, the differentiator is gonna produce a 0 volt, right? Derivative of a constant is a 0 volt. So the output will always be centered around 0. So your peak to peak is 20 volt, that means it is going from 10 volt to negative 10. So this is again an easy way to figure out output of your differentiator circuit. And the next video will be about the phase shift circuit.